Hi and welcome back. In this final week we will discuss triple integrals. Let's start with a quick recap on what you learned about integration so far. For functions of a single variable, you know that the definite integral gives you the signed area of the region below the graph of the function. For functions of two variables, you know that the double integral gives you the signed volume of the solid region bounded below the graph of the function. However, for a function of three variables, there is no immediate equivalent of this concept, since, as you know, it doesn't make much sense to talk about graphs of functions of three variables. In theory, you could consider the triple integral as a sort of hypervolume in four-dimensional space, but this interpretation is not very useful in practice. So why would you want to integrate functions of three variables in the first place? Before we answer this question, let's first fix some notation. If E is a solid region in R3 and f is a function of x, y and z, then we denote the triple integral of f over the region E as you can see on the screen. Such a triple integral can formally be defined as the limit of appropriate Riemann sums, but we will omit the details here. We can integrate over all sorts of solid regions, including, but certainly not limited to, rectangular boxes, cylinders and spheres. As to see why triple integrals are useful, let's consider the following situation. Suppose you have a solid object with mass density function ρ of x, y and z. We want to find the total mass of the object. In order to do so, we need to add all the mass elements dm equals ρ times dv that occupy a volume element dv. This means taking a triple integral of the mass density function over this region. If the mass density function is constantly 1, the total mass and the total volume have the same value. So that means that the triple integral of the constant function 1 represents the volume of the solid region. Recall that for double integrals we saw a similar result, where we showed that the double integral of the constant function 1 represents the area of the region of integration. Let's consider another situation where triple integrals might arise. Suppose an electric charge is distributed over some solid region with charge density function ρq. In that case, the net total charge within this region is given by the triple integral of the charge density function over this region. Since the charge density can take both positive and negative values, it makes sense to also consider triple integrals of functions that can take negative values. Several concepts we have seen for double integrals generalize easily to triple integrals. For a solid region E, the x-coordinate of the center of mass can be computed as 1 over the mass times the triple integral of x times the mass density function. The formulas for the y and z coordinates of the center of mass are similar. Finally, let's consider the moment of inertia of a mass that rotates around an axis. This is the amount of torque needed for the desired angular rotation around this axis. For a point mass of mass m, the moment of inertia is given by mr squared, where r is the distance to the rotational axis. Now suppose we have a solid object E with mass density ρ, rotating around one of the coordinate axes, let's say the x-axis. For any point x, y, z on the object, the distance to the x-axis equals the square root of y squared plus z squared. That means that the total moment of inertia around the x-axis should be the triple integral of the mass density times the distance squared, which then turns out to be the triple integral of the mass density times y squared plus z squared. The formula for the moments of inertia around the y and z axis are similar. That's it for now. Next time we will discuss some special types of regions which allow you to compute a triple integral as an iterated integral. See you then.